the following lesson, we will analyze a steel hose clamp as it bends around a hose with multiple simulations to highlight the difference between a linear and non-linear approach to solving problems. We will start by defining a linear analysis which will produce an accurate solution due to the non-linear nature of the simulated event. We will define a non-linear analysis and solve it with fixed time increments. We will define a second nonlinear analysis which we will compare with the first that we will solve with automatically sized time increments. Finally, we will explore solving the problem using the large displacement option available in static studies. The basic setup for the analysis in this lesson start with the hose clamps, which is 150 mm long, 113 mm wide, 0.25 mm thick and made of AISI 304 steel. We'll fix one end with the fixed geometry fixture and subject to other the 360-degree for rotation using an advanced fixture. The lesson assumes you have a basic understanding of SolidWorks simulation linear static module. In general, it is always good practice to start any simulation with the linear analysis. For this reason, I will start by defining a linear static study. I will browse the Command Manager Simulation tab and click New Study. I will keep the static module selected, name the study linear and click OK. Because this part contains sheet metal feature, the study automatically defines the geometry with shells. The material AISI 304 which was applied to the part is transferred to this study. I will prescribe a 360-degree rotation to one of the clamps end faces with an advanced fixture. But first I will restrain the other end. I'll right click the fixture node and select fixed geometry. I'll rotate the part and use the keyword G key to summon the magnifier. I'll select the end face and click OK. Now I will define the fixture that will rotate the other end. Again I'll right click the fixture made, but this time I'll click advanced fixture on flat faces. Using the magnifier I'll select the end face. Now I'll scroll down and define the fixture prescribed displacement. Starting with the transitions, I will activate a long face direction 2 and keep its translation set to 0. The other two directions will remain unconstrained to allow movement. Under rotation, I will activate all three direction components. Under a long face direction 2, I will enter 6.25 radius, rotating the face 360 degrees. We prevent rotation in two directions and translation in one direction to stabilize the model. Restraining auxiliary boundary condition increase the module stability when solving. However, this approach can also overconstrain the model movement, thereby preventing deformation that should occur. Finally, I will click OK. At this stage, I am ready to define mesh. I'll right click the mesh node and click create mesh. I'll expand mesh parameters and click curvature based mesh. I'll enter 3 mm under maximum element size, 1.5 mm under minimum element size. Keep 8 under minimum number of elements in circle and 1.4 under element size growth ratio. I'll expand advanced, ensure the mesh quality is set to high to use high quality elements and click OK. I'll right click the study name from the SolidWorks simulation study tree and select properties. From the option tab under solver selection, I'll keep the automatic option selected. Allowing the use software uses a solver based on the geometry and setup. Scrolling down, I'll ensure the large displacement option remains cleared. We'll explore how this option affects the analysis later in this lesson, but keeping it clear ensures the study solves the problem with a linear methodology. Now I'll click OK and run this study from the command manager. The study begins to solve before a warning message appears, suggesting we activate the large displacement option. Because this study aims to explore the linear solution, I'll click no and the processing phase completes. I'll activate the displacement plot which displays with a reduced deformation scale. To change the plot scale, I'll right click to its name and click edit definition. I'll click the true scale under deformed shape. Browsing the setup tabs, I'll activate superimpose model on the deformed under deformed option and set the transparency to 0.75. When I click OK, we observe how to linear analysis fails to simulate 360-degree rotation of the hose clamp's leading edge. A closer examination shows that the edge does not travel in the x direction, which follows a linear as small displacement theory as applied to shells. By definition, a linear study assumes a straight line relationship between the load and its structural response. If the load doubles, the results double too. This assumption forms the basis for how linear studies solve problems. When these studies solve, the software determines the structural response based on the initial stiffness, which never changes, and then applies the whole load in the one step. The linear study does not capture the full rotation because the load initially moves the leading edge down, which forms the linear trajectory and structure respond to the rest of the load. But in this case, the geometry and extension structure stiffness change and the load applies. The limitation highlights why linear studies produce accurate results unless the structure displacement is small compared to the parts geometry. The following video will explore how to nonlinear response accurately capture this model rotation. Let's explore the nonlinear solution to this problem. To save setup time, I'll right click the linear tab to bottom and click copies to study. Now I'll activate nonlinear under task study. Enter nonlinear under study name and click include mesh and click OK. A nonlinear study incrementally updates a structured stiffness while applying the load through an intermediate parameter called pseudo time. Pseudo time acts as the fourth dimension through which the 3D name. Pseudo time differs from physical time because it does not consider acceleration. The software updates the structure loading condition and stiffness with geometry and material consideration at each pseudo time setup. If then consider the step size and solve the linear static analysis to obtain an equilibrium solution by finding a balance between the applied load and the structure response to the load. Each step requires to solve coverage upon an equilibrium solution before proceeding to do the next time step. We define the relationship between the load and pseudo time with the time curves which they define the load property manager. In this study, the load is the on flat faces fixture. I'll right click on flat faces and click edit definition. Under variation with time, I'll click curve and then click view. The plot displays a linear relationship between the load and pseudo time. I'll close the graph and click OK. While we control load progression through pseudo time from the load property manager, we control the pseudo time progression through the study properties. I'll right click to the top of the tree and click properties. You under stepping options, we can specify the study start time and end time. We will keep at their default values. The software also present two options to control pseudo time progression: automatic and fixed. The fixed option allows you to specify a set time step from the start to the end. We will discuss the automatic option later in the lesson. I'll select fixed and enter 2, which means we will attempt to solve this analysis with 5 increments. Now I'll scroll down and ensure the use large displacement formulation is active. The option activate an algorithm and that updates the structured stiffness matrix based on the deformed geometry at every step. I'll select manual under solver selection and use the drop down to select Intel direct pairs. Now I'll click advanced options. The advanced tab appears and becomes active. Under method and ensure force specified the control. Remember the force control method solves for the response by controlling the load with time. This displacement control method solves the load given a control response, and the arc length control method control both of the load and the response and solve the relation between the two. I'll keep the remainder of the option to their default values and click OK. Now I'll click run this study from the command manager. I'm immediately present with an error. Let's try to understand the nature of these error messages as I dismiss them. At each load step, the solver attempts to find an equilibrium solution where the load and the structure response to the load are equal. In this case, the solver could not find an equilibrium solution because the fixed step size was too large. Decreasing the pseudo time steps may allow the simulation to solve. Therefore, I'll edit the study properties, enter 0.01 for the fixed time increment and click OK. Now I'll return the study which will solve the problem with 100 equally sized time increments. In the following video, we'll analyze the results and explore how to solve this problem with automatic time step increments. With the processing complete, I'll activate the displacement plot which displays with an accelerated deformation scale. In contrast to the result of the linear study, this study results show that the clamp bends as intended, animating the displacement plot marches through the 100 steps. This analysis solved. Notice that the deformed shape approaches the final solution in small, discrete steps. Let's explore another method for observing how its displacement changes with the time through the probe command. I'll explain plot tools from the command manager and click probe. I'll use the magnifier to help me select one of the corner vertices on the. Now I'll scroll down and click response. The graph shows how the bending action causes the end of the part move away from its original position and then move closer as it's bend around. Remember, standard displacement plots always display value greater or equal to 0. Directional displacement plots are required to observe negative values. I'll close the graph and click OK. Fixed time increments provide ideal post-processing data due to their equal size steps. But issues arise when processing these data. Choose a load step too large and the processor fails coverage and unequilibrium. Choose a load step that is too small and the processing time increase unnecessarily. For most studies, the ideal step size varies throughout the solution process. The automatic approach attempts to the process nonlinear studies as quickly as possible by weighing the step size based on the ease of convenience, using large steps when equilibrium is easily achievable and small step when necessary for convergence. This option provides parameters to control the step size through the algorithm. Let's create a new study that uses the automatic approach to explore how its results differ from the fixed approach. I'll right click the nonlinear tab at the bottom and click copy study. I'll transfer the mesh data to the new study which is named autostepping. Now I'll open the autostepping study properties and select automatic. Let's discuss auto-stepping studies. With automatics enabled, the initial time increment always determine the size of the first type. Subsequently, time steps increase or decrease based on the previous step convergence, but never exceed the limits defined by the max and minimum parameters. When a step becomes too large and the solver fails to find an equilibrium solution, where the structural response matches the load, the solver reduces the step size and it tries again. This process characterizes an adjustment. The number of adjustment parameter determines the maximum number of adjustment allowed before the study fails. Occasionally, a study may fail because it requires more than 5 adjustments, which is the default value, but these failures often signal the presence of a non-convergence issues. I'll keep the default parameters shown here and click OK. Now I'll run the study which solves this problem faster than the previous study. In the following video, we will analyze the results and explore how to solve this problem using the large displacement option available in static studies. Let's explore the result of this study which uses auto-stepping and compare the result to those seen in the nonlinear study which feature the fixed step approach. The default behavior for nonlinear study is to display results for the last solved step upon completing the processing phase. Additionally, an on-screen text display that we are viewing 61 step, which means that the analysis stalled. Remember, using the fixed approach, we solved 100 steps to find the end solution, which explains why this study ran faster. Animating the displacement plot shows the similarity between the two studies. Let's explore another method of solving this problem using static study with the large displacement option active. I'll right-click the linear tab at the bottom and click copy study. I will name this new study large displacement, copy over the mesh and click OK. Now I'll open the study properties and activate large displacement. Remember, the first linear static study failed to capture the clamp rotation because its reference to the structure initial stiffness to calculate an equilibrium solution. However, the large displacement option provides some nonlinear functionality to the linear static module, but it's no substitute for most nonlinear problems. For example, the large displacement option only solves large displacement geometric nonlinearities and does not solve material or contrast. Additionally, the large displacement option does not allow you to edit time stepping or load time curve. When I run this study, we see non-intermediate animation of the processed steps. The part final shape closely matches the results of the nonlinear studies. However, when I animate the plot, we see the final limitation of the large displacement option. Only the final step is available when viewing the results. Therefore, the animation does not show the clamps increment shapes between the initial. Finally, I'll save then close the part.